Hello, my name is Hector and I will present you the Orbital Resonance project. The main goal of this project is to highlight the effects of orbital resonance between two bodies. Basically, it's a major one, like a planet, and a smaller one, like an asteroid. And these two bodies are usually orbiting around a bigger one, for example, in this case, the Sun. Here in red you have Jupiter, and in black you have the asteroid Hilda. Hilda is in a 3:1 orbital ratio with Jupiter. That means that Hilda is doing 3 orbits around the Sun, while Jupiter is just doing 1. So as the main goal of the project is to highlight these effects, we need to do 2 steps. The first one, the bigger one, is to use simulink to propagate the two bodies or more using the Newton's law of gravitation. The mathematics are quite simple. Here they are. So you can see that the only force involved here is the gravitational one. And the second step of the project is to rotate the results in order that the camera is turning at the same speed as one of the bodies, and in this case it's Jupiter. As you can see, the orbits of Hilda in this reference frame is not an ellipse, is more like a triangle, and these are the effects of the orbital resonance, which is again 3:1 ratio. And let's now move on the simulink model. So here is the simulink model, which is pretty simple. If we assume that we know the acceleration for each particle on each axis, so the x-axis, the y-axis, and the z-axis, we simply perform an integration of that using the initial velocity values, which gives us the velocity for each particle. We perform a second integration using this time the initial position, and we now have the position of each particle. What we want to do is to calculate the gravitational forces due to the first body, which was the Sun in our case. So to do that we use this subsystem. Pretty simple. Here we calculate the distance between the attractive body and each particle, so it's here, and then using the body mass, the gravitational constant, and this distance to the power of 3, we can easily calculate the gravitational forces. We are outputting that here. And as we also want to calculate the gravitational forces due to the perturbating body, we use the same subsystem, but in this case, the position of the attractive body is the one of the perturbating body, so it's changing for each step, and we just have to select it here. So we perform the same calculation. We have the two forces due to the two bodies, and we simply add them on each axis and then close the loop. And here we are outputting each position of each particle at every step, and we will use this matrix for further calculation. The MATLAB script is very simple. Firstly, we have some preliminaries here. Then we set up the initial condition, so the time duration of the simulation, and we choose between different setups. Then we plot the first frame with the initial condition in order to check if everything is alright. After that, we are running the model and following by a quick post-processing of the results. Then we are rotating the results, and here we are plotting the results. Every time we plot the result, we are creating an animation AVI file in order to be able to check again the animation without using MATLAB and simulink. I will quickly show you this example here. So if we launch the script, we have the initial condition, here they are, and the animation. I am finishing this video by showing you this result here. So as you saw, the first shape was a circle around the Sun of 20 particles, and the perturbating body had the same mass of the Sun divided by 100. And you will see that the first shape, the circle, will quickly evolve in a big mess. Feel free to download the MATLAB script and the simulink model. The link will be on the description of the video. Bye bye!